My name is Jian Sun. I'm a software engineer from NCA. Today, I'm going to present some of our recent efforts about the GPU work. The title is Accelerating the Cloud Microphysics Parameterizations on GPU using OpenACC and OpenMP target offload. Before I move on, I want to thank the great contributions from John Dennis and Sherry Mickelson for their efforts on the work as well as polishing the slides. So first, what is cloud microphysics? Cloud microphysics is known as a small-scale process in the atmosphere that drives the formation and evolution of cloud and precipitation particles. It is closely related to many atmospheric phenomena and disasters, such as hurricane, storm, and hail. The figure on the right shows that the cloud microphysics is very complex. It contains more than 10 sub-processes. So as you can tell, it is very challenging to represent the cloud microphysics easily and accurately in the model. And even if we do so, it could be very expensive. There are many cloud microphysics parameterizations. The one we are exploring in this work is called PUMAS, short for parameterization of unified microphysics across scales. It is widely used in many atmospheric models, such as CAN, short for Community Atmosphere Model, used in this work. I want to mention that PUMAS is not a static code. It is under rapid development. So at the time we are working on this code, it contains about 5,100 lines of codes, about 60 subroutines or functions in total. Considering the fact that the total CAM physics source code has about 420,000 of lines, PUMAS only represents 1.2% of the CAM physics code, but it could contribute to as much as 8% of the total computational time. Therefore, it motivates us to think about this code and see if we can speed up in some way to save some computations. So the solution or the strategy we came out is to offload the computation of PUMAS to GPU. The reason is because first, the whole CAM code is already highly parallelized on CPU by MPI or OpenMP. Second, the PUMAS calculation is mostly column independent, which makes it a natural fit to the GPU computing. So when we do the GPU offload work, we don't begin within the whole model. Instead, we generate a kernel version of PUMAS, which is easy for code development and debug. The GPU programming method we use in this work is OpenACC and OpenMP target offload. Both of them are directive-based methods because it allows a single source code to be run on either CPU and GPU, achieves good portability as well as maintainabilities. And by using the directive-based method, we don't need to rewrite everything at once. We can incrementally port in the section of code to GPU, verify its correctness, and examine its performance. I want to note that in this work, we write all the OpenACC directives based on our knowledge, but we explore a tool developed by an Intel company to auto-migrate all the OpenACC directive to the OpenMP target offload, and it works very well. So after we insert the OpenACC directives, generally all the code's volume is increased by 10%, and we think it's a reasonable cost. So after doing the code development, we start to do the performance measurement. In this study, we will present two performance. The first one is showing in the kernel version. The machine we use is called Casper, which is a small cluster at NCA. On the CPU one, we use one compute node with 36 Intel CPU cores. And we test different compilers and find out the Intel compiler gives the best performance, and that will be used for the CPU simulations. For GPU, we will use 1 to 8 via 100 GPUs per node, and we use the NVIDIA's compiler that supports OpenACC 2.6 and OpenMP 5.1. Both is for the GPU offloading. And in this particular performance measurement, I will only measure the computational time on the GPU for comparison. So first, let's look at the comparison between 36 CPU cores against the 1 MPI rank plus 1 V100 GPU. The black line shows the CPU performance and the color line shows the GPU ones. X-axis refers to the number of columns per node or per GPU. Y-axis is the performance metric, where the higher value is, the better performance it will be. So the CPU performance drops quickly when we increase the column numbers per node. That is expected as we will have more and more cache misses with larger problem size. And for the GPU performance, it doesn't perform very well when we have a very small problem size. But the performance increases rapidly, and at some time when we have sufficient parallelism on GPU, it is able to outperform CPU. And in this case, GPU achieve about 3.7 times speed up compared to a 4 CPU node. And when we look at the OpenACC against the OpenMP target offload, OpenACC is about 1.2 times as fast as OpenMP in this particular case. And it is consistent for different problem size as well. So that is good. But in reality, the GPU configuration in the previous slides may be problematic because in the CAM infrastructure, if we use only 1 MPI rank for a particular parameterization, we have to use 1 MPI rank for all the other parameterizations as well. So as we know that only PUMAS is running on GPU, all the others are running on CPU. So using only single MPI rank will ruin the performance of all the other components, which is not desired. So the better solution is to use the 4 CPU node and oversubscribe the GPU with multiple MPI ranks. Fortunately, for NVIDIA GPUs, we can do that through the MPS service. So in this particular figure, I show the performance of using 2 MPI ranks launched on the same GPU by using MPS. So based on the bar plot, you can see when the problem size is small, turning on MPS improves the performance dramatically, which shows the benefit of using MPS as expected. When we have a larger problem size, the using MPS may not give us as much benefit as we see before because the problem size is large. Each MPI rank will always use so many resources, and the GPU may not be able to run multiple MPI ranks simultaneously. But anyway, we can see turning on MPS is benefiting for all the case. And in these particular examples, even if by oversubscribing the same GPU with multiple MPI ranks, OpenACC is still about 1.2 times as fast as the OpenMP target offload did. We can continue to do the oversubscribing here by launching up to 36 MPI ranks per GPU for the Casper machines. Here shows the result, and I only show the OpenACC one since it always gives the best performance so far. And we can see for the small problem size, if we are using multiple MPI ranks per GPU, it actually hurts performance significantly, especially we have 36 MPI ranks per GPU. However, when the problem size increases, the difference starts to eliminate, and at some point, actually using multiple MPI ranks per GPU beats the performance by using 1 MPI rank per GPUs. So this beneficially may be observed when we have sufficient large parallelism. But on the other hand, when we compare to the CPU performance, no matter which configuration we are using, GPU computing can still outperform at some point. And the issue of oversubscribing the same GPU with multiple MPI ranks could be mitigated to some extent if we have multiple GPUs per node. That's the case on Casper. So here we do the weak scaling, but use 1, 2, 4, and 8 GPUs per node in this case, showing as 4 color lines here. And our result shows that using 2, 4, and 8 GPUs could achieve 3.5, 5.8, and 8.6 times speed up against 1 GPU. You might be curious that why the speedup is not linear to the number of used GPUs. And the reason is because when we use 2, 4, 8 GPUs, they are oversubscribed by a different number of MPI ranks. As you can see on the previous slides, that will affect the performance a lot. So that's the performance we observe from the kernel version. We then go ahead to the practical CAM simulations, where we only run PUMAS on GPU, but all the others on CPU. Here we will test the 2 resolution configuration. One is low resolution, which refers to about 50,000 columns in total. And for the high resolution simulation, we have like 777,000 columns in total. For the CPU simulation, we still use the Intel compiler. And in this case, we will scale the simulation from 1 compute node to 3 compute nodes. For the GPU simulation, we do the same thing, and we will oversubscribe the GPUs by up to 36 MPI ranks per node. We use the NVIDIA's compiler, we only shows the OpenACC result in this case. And when we do the performance comparison, I will include both computational time and the data transfer time between CPU and GPU. Here's the result for the 1 computer node at low resolution. The blue bar shows the CPU result, and the other 3 color bars shows the GPU one. The y-axis shows as the speed up numbers, so the higher, the better. So when we only use 1 computer node, we can attain about 3.7 times speed up between GPU and CPU is when we use 8 GPUs per node. And we can see by using multiple GPU per node, it is noticeably beneficial when we compare like 8 GPU to the 1 GPU results here. However, when we increase the compute node used from 1 computer node to 3 computer nodes, we only observe about 1.4 times speed up, even if we are using 8 GPUs per node. And actually, if we only use 1 GPU per node, the performance of GPU is even worse than the CPU performance. This result is expected because when we scale up to a larger number of nodes, we are losing the parallelism per GPU, and that is actually very critical to achieve the best performance on GPU. So as a sensitive test, when we still use the 3 computer node, but switch from low resolution to high resolutions, we immediately regain the big speed up. And in this particular case, we actually observe the biggest speed up between the GPU and the CPU one, which is 5.4 times speed up when we use 8 V100 GPUs. So combining these slides against the previous slides, it again highlights the importance of achieving sufficient parallelism on GPU if we want to have a good performance compared to the CPU one. Also, another point is to show which part is critical on the GPU, computation or data movement. Here, I showed analysis of the time contribution to a GPU run from 1 GPU per node, as well as 8 GPUs per node. The x-axis shows using 1 node to 3 nodes, and the y-axis is the contribution. As you can see, the computation on GPU, represented by the blue color, only contributes less than 40% in this case throughout all the simulations, which means that the data transfer and the allocation of temporary variables on the GPU is more time-consuming than computation in this particular case, and that should be the focus of our optimizations in the future work. So as a summary, in this work, we have taught the cloud microphysics parameterization known as PUMAS in CAM from CPU to GPU by the directive-based method. So OpenACC generally outperforms OpenMP target offload by 20% in the standalone models, and the GPU simulation can outperform CPU simulation in a practical CAM simulation, even if we are using a low resolution configurations. Of course, the speed up is more evident at high resolution due to its larger parallelism on GPU, and we have confirmed that we can benefit from exploring multiple GPUs within the same computer node. The data transfer and allocation time are shown to be more expensive than computation on GPU for our particular problem, and we are working on the optimizations on that part. One thing I don't show in the slides, but I want to highlight is that NVIDIA provides awesome tools for profiling and visual demonstration, which is known as the NSAP system and compute tools. And I encourage everyone to explore it to help you understand your code and optimize it better. With that, I want to acknowledge the funding support from NSF Earthwork project as well as NCAP-based funding. And besides the co-author list on the slides main page, I want to also acknowledge the contribution from the many people from NCAP and outside NCAP. With that, I will stop at the reference line to our paper published this year about this work, as well as some tools we used. I also list my contact information here in case people want to initiate an offline chat or maybe future collaboration. Thank you, and I'm happy to take any questions.